we want to record these demonstrations for the students like you. Do you have a problem with that? Is that?
No, that's fine.
Okay, so the apparatus here demonstrates Faraday's law, which pretty much you have learned, right? So what happens is we have a coil here, which takes an alternating current, which is a varying current through the coil. And when there's a varying current through the coil, there will be a magnetic field induced. When the current changes, the magnetic field changes. So if we have another loop or a conductor close by, due to this changing magnetic field, there will be current induced in this one. So due to the current, when there is a current, like always electricity and magnetism go together. So when there's a current induced in this one, there will be a magnetic pole. So what happens? These two will become like poles, right? So they should shoot off. So we'll see if that happens. Okay, so another material. This is kind of heavier, so I have to be more careful. If the loop is broken, now in this case, if I put it, can an electron complete a circle in this one? So there can't be a current, right? There cannot be a current in this one in a loop, right?
Complete, yeah.
Then there cannot be a magnetic field in that.
So it's not going to move anywhere.
Yeah.
The battery went out. Is this the same idea behind the Hall effect?
It's kind of the same electricity and magnetism. There what happens is the electrons get attracted to one end, and then it builds up a potential in between the conductor. The same idea is very applicable in nowadays. I think even you are using wireless charging. So I'll show you one circuit here. So pretty much the concept of wireless charging, you have a coil like this in the charger, and you have a coil like this in your mobile phone or whatever device which supports wireless charging. So when there is a varying EMF here, it will induce a current through this one.
Yeah.
So using the same concept, we have that. Hall effect, it's not exactly the same, but if you go to basic theory, it's not like you have magnetic and electric effects there.
Well, yeah, but yeah. To be honest, I don't know that much about the Hall. I know name and general effect.
Okay.
I forgot what it was generally about when I decided to ask the question. But.
So now you know how your wireless charger works actually. So
Yeah, pretty neat.
yeah. So it becomes hot
Yeah, you gotta cool it down in between demonstrations. Yeah.
Yeah. So the setup is different in the wireless charger, but it's pretty much the same. So you have two flat coils. The device and the other. Any questions on this? Oh.
No, not that I can really think of, to be honest.
Yeah, it's simple but useful.
Yeah, simple but effective.
Yeah, of course. This one is not that efficient though, because it heats up.
Yeah.
It should.
So are you really interested in physics, or are you just kind of
Quite, I'd say.
Quite?
Yeah.
What made you interested in physics?
Good question, I guess. I guess I like knowing why things do.
Yeah.
I don't know. It's a pretty basic answer.
Was there anyone that got you into physics?
I'm part of my school's academic team.
Okay.
And I happen to choose science.
Yeah.
So physics comes with the job, and then.
Good start.
Yeah, so.
You plan to go to UofL?
Yeah.
Okay. Well, you're in a good place. So you learn about Faraday's law. Faraday's law is a very fundamental law in the realm of electricity and magnetism. What I'm demonstrating over there is what we call standing waves. What's standing wave? Are you familiar with? Have you had any classes?
I'm familiar. My school actually doesn't. We don't have a physics teacher this year, which is very unfortunate. So most of my education comes from me seeking it out. I know some of the math behind standing waves because I get asked questions about them.
Okay. Oh, sure. The idea behind this wave. So let's say we have a. I'm just gonna prepare something.
What? Yeah.
So for the idea of a standing wave, over here we have this pulley with this mass on the end of it. This pulley gives a string tension. It makes it, tighter, more strict. Like, well, up here it's a bit more loose. So the idea of this tension in the string, we can play around with its frequencies, and you know what frequency is?
Yeah.
So say that we have a wave going. Coming up, down, up, down. When it reaches this point, it comes back. And when two waves with the same frequency going in the opposite direction meet, they create what we call this standing wave. So by these standing waves, we can have all kinds of multiples of these. So we'll have a wave that kind of, might have, let's not start this one. These whiteboards never erase really well, do they? Them all. So say we can have waves, and they have like their counterparts. So we can set this up at a certain frequency, so that we have like 6 of these waves just standing. Let's see. So this is called a sine wave generator. What do you think that does? It generates sine waves, yeah. So this is our power source. This is our vibration generator. What do you think that does? It vibrates the string, correct. So we have an on switch. Turn this on. This is vibrating. So we have what's called amplitude. We can directly tune the frequencies. So what's the amplitude?
How tall it is.
Yeah. So we have a wave. Amplitude is basically the height from its point that it's moving, going about. So this will be the amplitude. These little points, these are called nodes. And we'll see that when we generate these standing waves at a specific frequency, we'll have these nodes in the middle. So, you want to try? Let's go to I'm going to turn the amplitude. It's going to get a little loud because it's using more power.
Yeah.
Here, you can turn it to maximum amplitude. All right. Now, I've already played around with this, so you can turn this knob till it's 68 hertz. So, right now we have standing waves. So we have like one here. You see right here where it dies down? That's our node. So then it does it again. We have 1, 2, node, 3, node, 4, node, 5, node, 6. Comes to this fixed end. So, do you think we can get less nodes?
Yes.
All right. So there's a next magic number. We call it 57. Go to 57. It's this one. That one just changes the decimal. Okay. 1, or how many is there?
Well, no.
5, right?
5, yeah.
All right. You think there's a pattern here? What do you think the next one might be? So what changed last time?
We changed our
frequency from 68 to 57.
46.
All right, let's go.
Wow. That's really cool.
So, how many is that?
4.
4?
If you count the end.
All right, what do you think the next one will be?
35.
35? You'd be correct. So there's not a lot of mass on this hanger right now.
So,
So if you were to decide to do physics here, maybe you'll be in the lab where I teach this, and then we could, play around with constant frequency, and then change the number of standing waves on this hanger by adding more mass. So the relation, if you learn when you go deeper in physics, let's use over here. So frequency. I love this whiteboard. Frequency for n number of nodes is n over 2L times the square root of tension over this fancy, like mu. It's called mu.
yeah.
So mu is what we call some mass per length quantity. It's simply just the mass of the string divided by the length of the string. So that value is what we call a constant. The value doesn't change, or it shouldn't, as we increase the tension and the frequency. So this tension, this is the amount of weight on the hanger. So if I increase this, I'll probably get a different frequency. See how it can change? Ooh, I'm getting 2 because I'm pulling down on it. But when I let go and get the tension, then we just get 3 again. So do you agree that tension has a role in this? All right. So we have this magical number n. We call these the harmonics. Harmonics. Well, it's really what we're doing right here. These standing waves, these magical frequency that the string can vibrate at to get these standing waves. How do you think guitars work? And like any other instrument with, so guitars and violins, they have strings, right? But they're fixed. Do you think they operate the same way?
I mean, yeah, they're tuned to that. Each string is tuned to that specific harmonic.
Yeah. So like on a violin, you can have what you call tune it. You're tightening it. You're increasing the tension. When you increase the tension, you increase the frequency. So when you pluck it at a certain spot, and you can make these notes, standing waves. So let's go down further to 2 standing waves. What number do you think that might be?
24.
24? Okay. Okay, we have 2. So this is what we call second generation. The second generation means 2 standing waves, but so really there's a pattern here. We're going down by 11, right?
11. Yeah.
So where do you think the first one might be? So this is where stability can have a play in this. So
Is this what's considered our fundamental?
this is our
frequency?
fundamental, yes. So maybe it's around 12, 1. 12 is a bit better. So now it's just 1 standing wave. This is very magnificent, pleasing. If we have lots of tension on here, we can make this stable. But for time constraints today, I can't show you that. So if you want to continue this, you have to come here. But if I add some tension right now, we could.
Are you a senior?
Yeah.
Congratulations.
So you might be coming here next year if you're interested.
So then so if 12 is our fundamental, then this is our first overtone then?
Yes. So and then everything after that can be like a multitude of that first one. But yeah, that's kind of a simplistic introduction to standing waves. Very good application. If you want to learn where the mathematics can come from, it can become very tricky really fast. They can come from something very, very complicated. So, are you more interested in the physics, mathematics, both?
Physics, more than
Physics?
mathematics.
Okay.
I mean, I don't mind math, but
That's good. That's good. Are you taking any calculus classes?
Mhm.
Okay.
um,
Well, calculus is all into physics.
mhm.
Every bit of it.
Yeah. My physics knowledge is primarily algebra based, but I'm in a calculus class.
Okay.
So, and calculus work in physics is significantly
Good.
easier than its algebra counterpart. So.
Yeah. Calculus is very, very useful.
Yeah.
Well, I hope you enjoyed this. This is, like I said, if you take physics, we can go more into this.
Thank you.
All right.
Is it like stations essentially then? Is that
Practically,
Okay.
we have like 3 stations. We have the Faraday's law, we have the standing waves, and we have.
Thermoelectric effect. Okay, I'm Bimal. So, do you know anything about like thermoelectric power or anything similar? No.
a lot of times?
Okay, so yeah. So basically, there are some class of materials. They can convert heat energy into electric energy. Okay, so we call them thermoelectric materials. So here,
Hi, how are you?
so here I have three samples of thermoelectric materials. So when there is a temperature difference between two sides of these materials, they produce like potential difference, because of which we get the current. Okay. So here I have candles, and then I have water, and I put like some ice in the water to make the temperature of the water more colder. So if I place this one on the top, and if I hit it from the back, the one side of these things here, this device, will be hot, and one side will be cold. Okay, so because of that difference, I will get some current. I have connected electrodes, which are wires, to these, and here is a small motor that will spin when there is a current. Okay, so let's see. Get more idea. So we do this one. Put this here. So now here is ice and here is a heat. Okay, so it will take some time to reach the heat here.
And heat it up
Yeah,
enough to
yeah.
get the current moving. Yeah.
Small kid stuff.
Oh yeah,
Yeah.
there we go.
Okay. So as the temperature increases on this side, you will see that will move faster. Yeah. So the condition here, this material should have temperature difference. Okay, if the temperature between two sides of this material becomes smaller, it will stop working.
Yeah.
Okay.
So then, how does the difference in temperature between the two sides, I guess, entice the electrons to move in a specific way?
Yeah, yeah. The electrons will move from hot side to the cold side.
So they're essentially picking the lowest energy.
Yeah, yeah.
That's
When
the
the
goal.
electrons get energy from heat,
The heat, they're
Yeah.
gonna want to lose it.
Yeah,
so
yeah.
Then, okay. That makes sense.
right. So the condition here, these materials, it is better if they are like less. I mean, if they are low, they have like low thermal conductivity.
Mhm.
So we want material that is high in electrical conductivity but low in thermal. Yeah.
Are those
So
similar
otherwise,
to
yeah,
what-
they will like conduct all the heat to the water, and eventually it will stop.
Yeah. Are those types of conductors generally a little bit harder to find?
I mean, no, actually. It's finding the best one may be harder, but yeah, we can almost all materials should be suited.
I was just wondering because, like, at least like from Kim, like generally, at least for the example of like most metals, the better they conduct their electricity, they're also going to conduct heat. So basically the same reasons.
So we can't like use them in like real life applications.
Yeah, it's hard to. I guess it's interesting that they pick that some materials will freely
So
conduct
almost,
electrons, but not really heat as a whole.
About all the metals are like they are both good conductors of heat and electricity. So they may not be the best choice.
Option for this. Yeah.
Right. So we can implement this technology in like to manage the heat in thermal management. So we can use waste heat to produce electricity.
Yeah. That's pretty interesting. It has really good applications, I guess.
If you go far in physics, you can find application in very, very many things.
Do you know how much this type of stuff is used on like a wider scale? Because then you also have to build. You can build more or larger modules. So then, how much does it?
So basically, there is a device named thermocouple, which is used to measure the temperature. So it is used in all vehicles, okay, to measure the temperature of the environment and also sometimes to measure the temperature of the engine as well. So so they are used more like detectors rather than as a power generator.
At a certain point, it's not going to continue speeding up anymore because
water is still cold and there is heat.
And the heat, you're going to hit a point where you can't increase the difference anymore.
Yeah.
Is this about where we are? Like, do you think it's going to go any higher from here, or I can't tell if it's getting faster anymore?
At some point it will be slower. Yeah.
You can make it faster by dropping the freezing point of water. Add some salt or something.
Yeah. That's another option. Yeah.
Thank you.
You're welcome.
Good luck in your studies.
Thank you.
I forgot to mention the other session. We have a very general, because of the total solar eclipse.
Yeah, that's coming up.
We have very one credit hour course open to everybody, high school students, teachers, and everybody. So it's just the faculty member asked me to mention this to interested students. So it's online next semester. It's also going on this semester, but it's online next semester. So battery students can take anytime if they're interested.
I'll definitely.
Yeah.
Thank you.
I think maximum is 24.
24 is the maximum.
Okay, wow, you got it right.
But we usually have less than that.
Yeah.
14,
Okay.
15.
Wonderful.
I try and have as many as I can. I like the pressure. You want to do?
Yeah,
Sorry,
get
your
started, introduce yourself, and
Maybe I will start from.
Oh, sure.
They're here.
yeah.
I'm Bimal. So I'm demonstrating thermoelectric effect. Basically, there are some thermoelectric materials. Those materials can convert heat energy into electrical energy. So to get electrical power from those materials, we need to have temperature difference between 2 inches of those material. So I have 3 samples. So what I'm going to do today is I will put water, it's a cold water, ice cold water on the top, and I'll heat the bottom part of these materials. So basically there will be higher temperature on the bottom part and cold temperature in the top. So with this temperature difference, it will create potential difference, because of which we'll get electric current on these wires. And here is a electric motor attached to these wires. So when there is a sufficient temperature difference, it will start working. Okay. cold water on the top. Yeah.
So cool.
Yeah, so this will work as long as there is a temperature difference. Okay, so when the temperature of the bottom part and the top part becomes same, it will stop working. So in our real life, we can use this technology to manage the waste heat. We can, like in industries, in automobiles, we have excess heat, right, which is wasting actually. So we can use this technology to produce electricity. So we can call it like thermal management. Also, from the amount of, if we measure the electric current flowing in the wires, we can we can calculate the temperature, okay, of this device. So we can use this technology to measure the temperature. Like our thermometers work in certain range of temperature, but these devices can work in very high or very cold temperatures. So all the automobiles, all the cars use thermocouples, which work basically indispensable.
Very cool. Very cool.
So, do you have any questions?
I remember there was something about this. 3 years ago, I did a state test, and one of the science prompts was about this type of technology, where it was I think it was the difference between like atmospheric temperatures in rainforests and the coolness of the ground, and the temperature in between there. They would lay pads on like the ground or hold them up, and the difference in temperatures would generate a current that would charge batteries.
Yeah, it's the same thing.
Yeah, very interesting. Very interesting.
Well, now you've seen it.
Yeah, actually, yeah. I was probably in 9th grade, so I was like, oh, okay, that's cool.
Awesome.
Yeah. So how long would you expect that to go for?
Yeah, it will go until the water here reaches the same, like until it's very hot.
Okay.
Yeah.
Have you timed it? Do you know how long that takes typically?
No, I have not.
I wonder, like an hour or like how long?
I guess
wonder-
like it will go at least 30 minutes. 30, yeah.
30
Okay.
minutes, okay.
Yeah.
Cool.
It's a great question. We should find an exact answer.
Yeah.
That's really cool. Thank you for showing us
Yeah,
that.
that is really cool.
Do you have another one? I mean, this is awesome.
Yeah, we have
Yeah.
two more.
Oh, okay. Thank you. Good job.
Well, I guess I'm next. My name's Jacob.
Hi, Jacob.
Nice to meet you.
Hi.
Nice to meet you. So how interested in physics are you? Are you a senior?
I'm a senior. Yeah, I'm looking in like medical degrees right now.
Okay.
Like they do require a certain level of math credits,
Oh.
and so I think one of those is a physics.
Okay, well,
so,
maybe there's a chance for this theory used in physics.
yeah.
I would also say we have a BA in pre-med within physics.
Oh, you do? Okay.
Yeah, it's not BS, but it's a bachelor's in science.
Okay.
Pre-med, targeted towards students who want to be pre-med students. So they'll take a lot of biology courses and stuff like that. I have you can start and I'll plot some
Okay.
information for you.
Yeah, no, there's lots of applications of physics and medical schools. But come to physics at university. So what I have today is a string. If we come in here, we have a little hanger with some maps on it. So in principle, we can add. So what do you think happens when we add more mass to this? Here, let me alleviate this. The string comes a little loose, right?
Pressure of the string's going to increase.
Yeah, the tension of the string is going to increase.
Tension.
Yeah, so here's a relation where pretty much for this one we have tension in this finger on this pulley, and we have the string meeting at this fixed end. So we have what we call a vibrational generator. What do you think that does? It creates vibration in the
Generates
string.
vibrations.
The string's going to vibrate at some frequency.
Okay.
What's frequency?
It's like the rate of something.
Yeah. The number of cycles per second. Per second is the important rate per second. So here we have a sine wave generator. Do you know what a sine wave is? Yeah, exactly. So that's pretty much what this does. This is going to generate sine waves. So imagine this top part. We generate waves that go up and down.
Is the tension going to help create different?
Oh yes, yes.
Hold on, it's been a while. different wavelengths of sound waves.
Yeah. So this board isn't the best. These markers could be better too, but we generally have a wavelength that's represented as 2 times the length of the string divided by n. What's n? Well, I'll show you. N is the number of notes. What's notes? They're these fixed points in the string where they don't change. So let's go ahead and begin. This is the amplitude. We can adjust it. I'll let you adjust it to max. Just turn it clockwise all the way. It's getting louder because it's using more power to it.
I can see it in my eyes.
Where is the noise coming from the box?
It's coming from over here.
Oh,
So
okay.
this is creating vibration.
See how it's,
Oh,
there we
okay.
go.
So this is currently at 100 hertz. What that means is that there's 100 vibrations, like waves going down it
Per second?
Yeah. So specific frequencies measured in hertz, we get what we call standing waves. So we can explore this. So I'm gonna go ahead and cheat and tell you to turn it to 68 hertz. This one.
Turn this part.
Yeah.
Which way? Just.
Oh yeah. Yeah.
Oh, okay.
Yeah. So you can turn it slowly, watch it slowly evolve.
What? Sounds like an airplane.
Yeah.
Landing.
Yeah. All kinds of fun
Yeah.
things happen when things touch.
There's 68.
So let's see. Maybe we can mess around with this. Here, let's turn this all the way. This increases the amplitude of the wave. The
So
amplitude
we
is,
can see a little bit more.
yeah.
Look at that.
So these waves. So how many are there? So there's 1, 2, 3, 4, 5, 6. So we can vary these numbers by adjusting the frequency. So I know you can't read my horrible handwriting and the light, but we can generate these numbers with this relation. So you'll see that a pattern can emerge for less and less waves. So right here, see this part? That's what we call the node.
The node, yeah.
So this is the part, where it's not really changing. So as these are coming down, these are creating these are interference. So interference is just a combination of waves where they come together.
So it's perfect in the very center. This isn't perfectly still. Is
Yeah,
that?
exactly. So waves traveling down come to this end, and they travel back, but there's still waves coming this way. So when they come together,
That's not perfectly still. It's vibrating.
oh well,
The very
node.
center, it's not going to move as much as
Right,
the
right,
middle
right.
of the wavelength.
Are they always interspersed evenly?
yes. So this is what we call a pattern of waves that emerge from these specific frequencies of the string. So this can vary with different strings, different lengths, masses of the strings, different tension in the string. So in a fun world where if you're in my lab, we could keep this frequency constant, and we could adjust this by adding mass to that string. So we could add a few weights, more and more weights, until it looks like we're hanging a backpack from here. So, but in this simple case, we'll just adjust the frequency.
Okay.
So I'll let you change the frequency to 57.
It's pretty.
So what? That's 5. We changed the frequency from 68 to 57. So that's a difference in 11.
Yeah.
So do you think the same effect will emerge at 4?
So it would be 46.
Yeah, let's find out. Let's see. Not very stable, but
But it's keeping 4.
it's remaining consistent. So we can continue this down to what we call the fundamental generation. So we can slowly go down if you want, or if you want to stop here.
You want to do 35. It's going to be very unstable now. but still three different sections, 2 notes.
So, usually in my lab, when I teach this, we keep the frequency constant and we change the mass. With
Okay.
more and more mass, it's much easier, but we could change it with.
Can you accomplish the same thing if you add weight to the string?
Yes, yes,
Okay,
yes.
okay, yeah.
More
We'll
weight.
show them, yeah. when we
Yeah.
run. Yeah.
Yeah.
More
that,
weight.
That makes sense for some
Yeah.
reason.
Increases the tension.
More weight,
Yeah.
more tension.
Right.
More, yeah. This is very nice.
So is it like, I can't remember what it was called, like an inversive relationship, the more tension, the less required frequency?
Yeah, so, well, it's proportional. So this is our frequency.
Uh-huh.
This is our tension. So it's under a square root. So yes, more tension, the more frequency. So we can adjust this for the number of nodes that we want. So we have some frequency. So we can multiply all this over. So let's see, 2L and divided by square root of T over what we call mu equals N. So let's see, 2L frequency. Let's change this. So yeah, our frequency will go down. Well, let's see. So let's go down to 24, maybe. Let's see if we can reach the fundamental generation. So it's not so stable, but that's okay. This is just this a bit. So in acoustics, like instruments, like guitars, violins, you have these strings that are fixed at 2 ends. You unplug them, and then they make this frequency of the sound. It's really harmonics is what we call it. These overtones, they're very delicate in nature. That these patterns exist. So let me take this to 13. It should. So this is what we call the fundamental generation, where it's just one singular standing wave.
Oh.
So if there's, say, 12 hertz of frequency, does that correspond to like, let's see, if we are each of these, I don't know, what's
Yeah.
the unit? There's 6 units of mass on that end. Is that what it's
Oh,
doing, or
oh.
what is going on with the 2 times the length?
Oh.
Or is that L?
Oh, this
This
is
first
just
one, yeah.
Yeah, this is just our relation for frequency that
Okay.
can derive for for the velocity of some wave traveling on here. If you would like to know more about this relation comes from physics and all the partial differential equations emerge.
Oh my gosh.
You can solve all the fun stuff where
All
this
the fun
comes from.
stuff.
Very cool.
We
I
can
can't
sign
tell
you up today.
but I can advertise.
But you can teach me.
Yeah,
next
I
fall.
can teach you. But in order to teach you, you have to come here.
Thank you.
Yeah,
Good
thank you, that's
job.
cool. All right, see you now.
Can I have a question about, is there an application for yours to manage greenhouse gases, like to use global warming?
This is used, waste gas, for instance, can be converted into electricity. That's the application.
Okay.
Like even, cars and stuff. There's a lot
Yeah,
of that,
right.
Yeah,
Well, you mentioned cars, and I was just thinking
Yeah,
the heat around the earth,
yeah.
there's so many negative things about it, but if it could be collected and, I don't know, I just was wondering about if energy cannot be created
Can that be converted
into some kind of clean, like using greenhouse gases or the heat, I don't even know what you would call it,
Yeah,
the negative thing to create some positive, like an energy
right. It is. Yeah, you can always convert one form of energy into
to another.
Yeah.
That's gonna make you famous one day, and it's on video.
So, have you ever heard about, I think you should have learned about Faraday's law and all, right?
At some point, yes, I have. It's been a few years, but yes.
Okay, so this instrument here, we can use this to pretty much get an idea how Faraday's law works. We have a coil here, which is woven around this rod. When I turn this on, what happens is an alternating current, what is an alternating current?
I do not know.
Okay, so there's a big difference between direct current and alternating. Like if you have a battery, you get a constant current flowing through the circuit. But whereas alternating current, it fluctuates like back and forth like a wave. So what we have in our main lines, it's all alternating current. But our electronics work with direct current, so we usually have to convert that into direct current. In this case, there's a varying current, which is like a changing current going through the coil. When there's a current in a coil like this, there will be a magnetic field created, right?
Right,
So
right.
when the current is changing, the magnetic field there will be changing. So if I put a conductor like this here, what would happen when there's a changing current in the coil? There will be changing magnetic field or changing flux. That would induce a
Is it gonna go up?
no. That will actually induce a current in here,
Oh.
which will induce a magnetic field here. So light poles attract or repel each other. So if that happens, if there's a current created in this loop, it should just pop out, right? So be careful a bit. Okay, I'll use it.
I'm gonna step back.
Yeah,
Okay.
step back, please.
Fair
Okay,
warning.
so let's see.
Okay, that's cool.
So it pops out, and even you can see this is actually heavy, right?
Yeah.
So I don't want to turn this all the way down. And we tried that in the morning, and it went all over.
Uh-oh, there's a mark on the ceiling. Has this happened before?
Oh, we were hoping you wouldn't notice that.
So, but question of the day: if I have this thing like this, when there's a changing magnetic field,
Would it not go?
Can-
There's a break in the
Because
current.
it breaks the
yeah,
current.
you can't create a circular current, like electrons can't complete a circle in here, right? In that case, there won't be a magnetic field created, right? So can this go up?
No.
It doesn't.
That's so cool.
Any idea about an application of this one? You
Launching
should be
into
using.
space.
Well, I was like, yeah, rockets.
No, you
No?
basically okay. After seeing this, you might. So this has a coil here.
Okay.
This has a coil here. So due to that changing magnetic field, you induce a current in this coil. So look what happens.
Oh, okay.
So, like the induced current is used to, like the EMF induced is given to the bulb, right? So it lights up. I'm pretty much sure that you should be using this sort of a thing. You have wireless chargers, right?
Yeah. Yeah, I have.
So
I use
it's the
those.
same concept.
That is
you
so
have,
cool.
You have a coil there, which creates a fluctuating current, and you have a coil in the device.
I have one. It's two different spikes.
Okay,
Is
that
that
is like
different?
that is a contact thing.
Okay.
So, for example, if you have an iPhone kind of a thing.
Yeah, my cell phone does that too. Like I sit it on a pad and it.
Yeah, for example, like I can show you this. Nowadays, like this has a. I think you might.
Oh
have
yeah,
taken-
I do the wireless power shit.
Yeah.
Yeah.
It's the same concept.
So one creates an alternating current for the other.
Yeah, like one access this coin, the other one access this
That
one.
is so cool. I didn't know our phones were doing that.
Would it work if it was a square?
As long
As
as,
long as
you
it's closed,
yeah.
that's all.
As long as it's closed.
Yeah.
Doesn't matter the shape.
No.
That's-
It could be a triangle as long as it's closed.
Mom,
Yeah,
have you,
all
have you
is
seen this
closed,
before?
yeah.
No.
Put your phone on. I should show mom.
Did you turn
Yeah.
it on? I think I might have.
You might have to turn yours on.
I might
Oh,
have
what
to
does
take
it repel each other?
Yes.
No, it won't pop off. Don't worry.
My phone can charge
Yeah.
his.
Oh, I think I knew that could happen, but I've never seen that
Yeah.
happen.
So it's the same concept.
Yeah.
So physics is basically what is used. So it is prevalent everything,
Yeah.
whatever we do, right?
Yeah.
In our everyday life, it is impacting. So the physics it looks like a very fundamental stuff here, but then day-to-day applications
Yeah.
we are using everywhere. That's what.
That is why. Okay. Now I understand. If you look at like, for example, his cell phone or my cell phone, there's a metal coil on the top of the battery.
That is the
right
coil,
here.
yeah.
Okay, so if there was a cut in that metal coil, then it would not wirelessly charge.
Yeah.
That is interesting. Very interesting.
Like same thing. Like
Yeah. Very cool. Very cool.
So neat.
This is Faraday's law.
Okay, speaking of Faraday's Law, have you seen the show Lost? Daniel Faraday is a character on Lost. He's
Yeah.
a physicist.
And who basically time
He
travels.
time travels. So
What about Oppenheimer? Who has seen Oppenheimer?
Oh, I haven't seen it.
I just
Yeah.
watched the movie.
Oh, yeah, but the H-bomb, was it, or an A-bomb? H-bomb.
H-bomb.
H-bomb, yeah. My husband went to see it, but I didn't go.
Okay, full of physics.
Yeah.
Yeah, no, that.
Well,
that-
this is
that
so
was
fun.
interesting.
Thank you.
right.
Yeah, good job, everybody.
Good, thanks for stopping by.
Yeah, thank you for sharing this with us. Hope your semester goes well.
And this isn't all physics. There's a plethora.
Yeah.
You do this all day, but we only take it till the fall. Gotta go.
Awesome. Y'all have a great day.
Y'all have a great
Thank
day.
you.
Bye-bye.
Yeah, you can start.
Yeah.
So,
Please introduce yourself.
yeah, so I'm Isuranga. Probably if you join, I would be there for like 223 lab.
You can come right up. He's like, you
24.
can get real too.
So, pretty much you'd be doing these experiments with the creator of Bimal. So, you might have heard about Faraday's law already, right? You know what that is. So, this is like a demonstration for that. You have a coil here. You know the difference between alternating current and direct current?
No.
Okay, it's like, okay. Current, we have two types, alternating and direct. So direct current is what you get from a battery. Then you just plug it into a wire. Alternating current is pretty much different, where the current varies like sinus, like a sine wave. So it goes back and forth. Whatever we get in our wall plugs and houses, that's alternating current. So the thing here is like here we have a coil woven around, and when we turn this on, supplies a varying current to this coil. So when there's a change in current in the coil, there will be, when there's a coil and when there's a current in it, there will be a magnetic field, right? But if the current is changing, the magnetic field will be changing. If we put another coil, due to that changing magnetic field, there will be a current in this one. Okay? Current induced. So when there is a current induced in this one, there will be a magnetic field induced, which is of the same form. Like fundamental rules, like which you should have learned around, I don't know, in primary grades. Like poles attract and like poles repel and opposite poles attract, right? So if this creates like if the induced current causes a magnetic field which is of the same pole, what should happen? It should pop out, right? So be careful. I will suggest, yeah, it won't be. Yeah. So let's see what happens. That goes on. This is actually heavy.
This is kind of.
Yeah. So what happens is, because of the magnetic field, this creates a current circulating around the loop. And because of that loop, you get a magnetic field.
Come on in.
It's like a generator on
You can gather around. This is
an alternator.
Yeah, it's like
Electromagnet.
in this case, it acts as an electromagnet, and you get the same sort of concept in transformers also, where you have one coil woven in one side and the other coil woven on the other side. When there's a changing current in one coil, it creates a changing magnetic field, and so it creates a current in the other coil, which is not connected to anything. So, like Faraday's law, there's a changing current here, which causes changing magnetic field. It creates a current here, and which supposedly creates magnetic field, which so it pops out because they are of the same pole. Now if I take this one, this creates a magnetic field which is changing, but can this one create a current like in a closed loop? No. So if I put it here, there won't be a current induced in this one, so there won't be a magnetic field from this, right? This shouldn't. That won't go on.
Because it's aluminum?
No,
No, because
Oh, it's a gap.
it's an open loop.
Okay.
So the loop should be closed for it. Now, a practical application. First I'll show you this. So what we can do is, we have a coil here, we have another coil here. So if I turn this on, So the changing magnetic field, so the alternating current here creates a changing magnetic field, so that changing flux induces a current in this coil, which drives the bulb to fly. And the same concept if you go for an application. I think you might be using this already. We have like in wireless charging. So we have same sort of concept, but this is like a tube-like coil. This is flat coil. So you have a flat coil in the wireless charger. Whatever the device you are going to charge, which supports wireless charging, has a coil in the device. So like it happened here, it induces a current in the coil which is in the device. It charges the device. Cool. You can pretty much learn about it. I mean, it's a simple thing, but useful. That's
What's your name?
I'm Isuranga. Nice to meet you all. So, any questions about this?
Are you a student here, a professor?
I'm not a professor actually. Like all of us are like graduate students.
Oh.
So I'm in the second year of my PhD.
Wow.
So
What's about?
I'm more into computer simulations and stuff like molecular dynamics and physics. There we have experimentalists. So Jacob is also in the second year.
Oh yeah.
And Bimal is senior actually. So if you come into physics, we'll be taking your labs in the second year and first years, right? So we'll be there to do all cool stuff.
Well, thank you.
Well, I guess that's much fun for me. So are you guys interested in physics? Or are you just,
We're just here to.
Sure. So, what are you? Are you interested in physics?
Yeah.
Are you a high school student? Are you a senior? Are you thinking about coming to here? Okay, well, this is my time to advertise to you. So, we have a nice simple string, orange string. But so things in physics or real life, they vibrate. But they vibrate with some frequency. What's frequency? It's the number of like cycles per second. Say we have a circle. We go around the circle so many times per second. Per second is the important part. So here, our demonstration is what we call a standing wave. So what's a wave? Like waves, like ocean waves. How they have different kinds of patterns. You throw a rock in a pond. You see the interference patterns. The different kinds of waves. They add together and they go in a radial direction. So. Oh, it smells like burn.
Yeah.
Okay, that's the next demonstration. So here we have what's called a sine wave generator. Do you know what a sine wave is? Very cool. So what do you think that does? It generates a sine wave, yeah. What about this vibrational generator?
It vibrates.
It vibrates the string, yeah. So this is what we're gonna do. You want to come over here? You can get a hands-on experience. So, the first thing we want to do, this is always easy, we want to turn this on. So you can do the button, switch. All right. So we have what's called amplitude. You know what amplitude of a wave is? Yeah, it's not the height from it, it's equilibrium. All right, we have frequency. You know what frequency is. Hertz per second, that's the unit. So we're at 100 right now, but it's not vibrating, but it's on 0 amplitude. So let's increase the amplitude to the maximum. It's gonna make lots of noise. All right, that's at the maximum. So in nature, objects have what's called a natural resonance frequency. So when you disturb it, they vibrate in some fashion. So if we pick a specific frequency, I'm going to cheat and just tell you, pick 68 as the sine wave. So we can turn this clockwise to go down. Just this. 69, 70, 71. And this was string before, so I kind of we have these waves, and they're, I think 7 is a good one. They look like they're standing. It looks like an optical illusion. But it's really just, so this vibrational generator down here is sending waves all down the top, and we hear it comes back downward. And this process is going back and forth. So eventually, two waves with the same frequency, they're going to meet. And when they meet with the same frequency, they can produce this stationary standing wave. So these parts right here, these are called our nodes. These are the points that don't really, move from their equilibrium position. So, do you think we can go lower than this? Do you think, let's see, how many are there? 1, 2, 3, 4, 5? Think we can get 4? So, let's go down to, maybe, let's go down a little bit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So about 4 emerge. Let's go to 14. So that difference, 14. Remember that. So how many do we have now?
4.
We have 4. What do you think will happen when we go to 3?
Yeah,
Which frequency?
Go down 14.
Go down 14. I'll let you do that.
3.
So this happens because these what we call harmonics. If you're interested in instruments such as guitars, violins, anything with like a string that is being held by tension. This is really like what we hear in music. We can pluck these strings and they come out at these harmonic generations. So these standing waves are very applicable. One application you don't want is the Takamo Bridge. This is a famous bridge that you'll kind of watch. This is not what a bridge is supposed to do. So this bridge is kind of resonating at a certain frequency. So bridges, paper, anything vibrates. There's this famous quote that in physics, there's this simple harmonic motion. Everywhere, everything vibrates. It's very fundamental in physics. So, you want to get 2? Bit shaky now. So, do you think this weight at the end of the string has anything to do with this? Do you think if I take the weight off, anything will change?
Take the weight off, it will just fall off. So.
Oh no. So we know that tension does have an effect on the string. Do you think the frequency changes proportionally? Inversely proportionally? I'll leave that to you to come to physics and learn about that. That's among the many other things that you can learn. So there's a more important one. It's called the fundamental generation. What do you think that one is?
It's fun.
Fundamental 1. Let's try and get 1. Let's see. Try to stabilize this. Maybe this is. I think that's pretty good right now. So usually in introductory physics labs, this would be a lab that you would do, except it won't be as easy as just turning a knob. We would make you have a constant frequency. So say 30 hertz. We would make you keep the frequency at 30 hertz the entire time, while we also try to get these other standing waves. So we'll go to 6, 5, 4, 3, 2, 1. So, how much mass do you think? So, to increase the tension in this string, come over here. We have a hanger. We place mass on it. Do you think it's a lot of mass to get the 1?
No.
No?
Maybe.
It's a lot. I don't want to spoil the fun. I want you to figure this out. But yeah, this is very fundamental. Does it almost look like an optical illusion? Does it look like, there's two streams? There's only really one. If you take your phone to it, your phone may not have a strong enough capture rate to record it. So if you try and actually get out your phone and record it, you might just see it just kind of going up and down, not this effect that we're all seeing right now.
Is it because it slows down to stop it?
Well, it's going at a particular frequency. Your camera works, it captures at a frequency. So it captures like so many frames per second. That's the frequency. This, same kind of thing. But on your phone you can adjust it, if it has that feature. And you can record this. But yeah, this is basically a standing wave on a string. You can do this with any kind of string.
What happens if you put weight on it?
Well, let's test that. Let's take this to 30. Let's keep it at 60 and I'll beat the tension. Try and pull it. So I'm pulling a little bit on it, and then going back and forth. The more I pull on it, then it's kind of more stable. Pull a little bit more on it. Kind of hoping the string doesn't snap. This is always kind of scary. Pull it a bit harder, more stable. I don't know how much I want to pull more to get the one. Yep, kind of moving it. So you can kind of imagine how much weight and tension. Well, weight is can be a tension. They have put on this to get the one. I was pulling down on it just to get it 2. Imagine it started moving. So yeah.
Okay, everybody spin.
Yeah. So I'm Bimal. I'm a project administrator. I also teach. I'm a teaching assistant as well. So today I have 3 samples of thermoelectric materials. Basically, thermoelectric material are those materials which can generate electricity when there is a temperature difference between 2 ends of the material. Okay. So I have a flat material. So if I heat one side and if I cool another side, there will be a temperature difference between 2 sides. Because of that, the electrons move from hot end to the cold end. So the motion of the electron is basically electricity, right? So we get electric current out from the device. So I have attached an electric motor. So when it generates the electricity, it will detect. When it moves, it confirms that there is electricity. So for that, I have some candles and cold water. First, I will place this cold water on the top, and at the same time, I will heat this one. It may take some time to reach the heat from this material to that. So now there is high temperature on the bottom and there is low temperature on the top. Because of that temperature difference, there is electricity on these wires, and because of which the electric motor is moving. So here the concept or this technique can be used in managing the waste heat. So in industry and in vehicles, in many other applications, we have excess heat that is going or that is wasting in the environment. So using such technology, we can use that to create the electric power, and we can, even if we store that one, we can run the vehicle. So and there is another application of this one. So the current here depends on the temperature difference. Okay, so we can use this concept. Once we measure the current, we can use some mathematical calculations and find the temperature. So there is a device called thermocouple. So that has two probes and there is the tip. So that device is used to measure the temperature. Okay, so that every materials show this effect. Some show high, some show low. So we'll get an electric current when there is a temperature difference. Okay, so if the temperature of either sides are equal, it will not generate any electricity. So we need a device, we need a material that can conduct the electricity but insulate the heat from one side to another side. So most of the metals show these effect, but they are good conductors of heat as well. So they they carry heat through one end to another end, and at the end, after a few seconds, there is the equilibrium temperature and they stop working. So for this type of device, we need to find the materials. We need to find ways to get highly conducting materials electrically but insulating thermally. So that's the research, that's the one research that is going on in this university. So there is an exhaust system in the car, right? So if we can attach one end of this device to the exhaust and another to the air, there will be some temperature difference, right? We can get the electricity from there and we can use that electricity to charge our vehicle. So this can be the real life application of this technology. Alright, so that's all I have for now. So do you have any questions? Yeah.
What's the material?
So they are called like thermoelectric materials. So it's Seebeck effect. So you can use we can use any material that is electrically conductor. Okay. So we can use iron. So if you use iron, you should have a very long wire, one at the hot end and another at the cold end, so that the temperature from one doesn't go there. For this type, we are using some kind of alloys, using two different materials that can have the property that can be less conducting for the heat and high conducting for the electrons, or basically for the electricity.
So is this what your PhD is about?
No, actually. I'm working on some other system which is called pyroelectric material. Okay, thermoelectric materials and pyroelectric materials are basically, they work in the same principle. I mean, they have same purpose, but they work in different principle. Like pyroelectric material also converts heat energy into electrical energy. This also converts heat into electrical. For these to operate, we need a temperature difference between two ends. But for the pyroelectric materials, we need temperature difference with respect to time. So the material can have the same temperature throughout its surface, but it should, let's take at the first second, if it is hot, it should cool down and go. So there should be a heating and cooling cycle to get electricity from that material. So it's like when it's heating, it creates the polarization of particles in one direction, and when it's cooling, it changes the polarization in other direction. So from that we get the electric potential between two ends of the material, and from there we take electricity. That for that material to work, we need heat for a second and then cooling for another second. For this one, we need heat difference between two ends. So yeah, they both can be used in thermal management part. Any other questions? No? Any other questions from you, Jacob?
Did we persuade you? Well, come here, talk with us. You will learn a lot.
Yeah.
What's your research?
Well, that's pretty similar to his. He pretty much said everything that I'm starting. So, but you can use applications from all fields of physics, you know, to do things that aren't even, you know, that we don't even know about right now. There's so much that we don't know. You may think that we know like everything, but we don't. The further you go, you realize we know nothing. But we can still use the stuff that we know to figure out what we don't know.
Yeah.
Yeah, I mean, we are working in the same project.
Yeah.
So do you need a lot of weight? Because this is kind of like a lever, like a simple machine.
Oh. Do you need a lot of weight?
Yeah. Is that why you need a lot of weight?
Well,
It's like a pulley.
let's see. Yeah, because this weight is not here, then it's gonna be kind of hard. But you know, so pretty much we want like a fixed, you know, string that, you know, is the same like across, you know.
It's hard to like pull this direction, but it's really easy to.
Oh yeah. But we have you know, lots of, you know, mass on one end. Then, you know, it's like a plane right now, so we can see the vibration be fairly easy. But if it's like down here, then it's kind of bumping against the table, and every time you touch something, that's friction, energy loss, vibration. So energy is directly correlated to vibration. So this is friction's the energy. Yeah.
Thanks.
You're welcome.
Hey guys, we appreciate it.
What's your name, Logan?
Very interesting.
I'm Jacob. Nice to meet you.
Thank y'all for coming out.
Thanks for having us.
We're glad you found it. We
Yeah.
almost were closing.
We
Quite literally.
We didn't see much cool stuff today till now, so.
All right. Well, they look forward to having you in the program.
Yeah,
All right. Thank you, sir.
okay.
Man, you did a good job.
I went out into the campus and I said, come, you must see these physics demonstrations. The best yet. This will be the highlight of your tour. Come, follow me.
You even got the staff to come. All right. Good job, guys.
So they were the organizers? I guess.
I think they're just helping out.
One of them is changing his major. The one with the red hair.
I wonder.
No, he told me. You don't tell somebody something if you don't do it.